Hi guys, I just missed out two very important points in the videos that I posted right now. One is the definition. I told you I'll be covering in the next one of the next videos, but I forgot about that. The dynamic range definition. So I define the dynamic range as, if I want to measure the dynamic range of a receiver, the minimum level that you can apply, that you can sense, the receiver can sense. It's called the sensitivity. Okay. And we know how to find sensitivity. I've extensively covered in the video and even in the lecture, so you can go through that. And also you can refer to chapter 2 of Razavi. He covers that extensively. Now, once you know sensitivity, then we said to find the maximum input level, we said we'll find the 1 dB compression point of the receiver. Then the dynamic range is simply the difference between these two power levels. Okay, the 1 dB compression point in decibels minus the sensitivity in dBm. I mean both in dBm. If you take the difference in dBm, you will get dB. So that will be your dynamic range. The other definition, which is called the spurious free dynamic range. So what are we going to do is that we'll apply two tones. Okay, so understand the minimum level is still the same. It is actually the P sensitivity. That's the minimum. The minimum level is always fixed. The maximum input is, the definition will change. The second form of dynamic range is what we call SFDR, the spurious free dynamic range. It's given in your textbook as well. I've used the same terminology here as well. So what do we do here is that your signal of interest will be lying in around the carrier frequency. That's the frequency there, and your interferers will be slightly away from the carrier frequency. As I keep increasing the interferer power, the two-tone interferer power, okay, at some point what will happen is that the interferer power will keep on increasing. At some point this interferer power will become equal to the noise, the total integrated noise at the input. Remember, how did we compute that? Your integrated noise was simply KT into B times the noise figure. So that was your total integrated noise of the receiver, okay, including the antenna's radiation resistance, noise and all that, right? So this is your total integrated noise. When your input level, when your the signal power here is, I'm going to call it P interferer, Pi dBm in dBm, okay, or let me just write Pi as the interferer power. When I keep increasing the interferer power, the intermodulation term power, this is the intermodulation term. When that intermodulation term power becomes equal to the noise power, at that point we stop it, and that value of difference between the power to the sensitivity. So this definition is, see, sensitivity is still the lower level, and we know the noise, integrated noise, is lower than the sensitivity, right? If you remember the previous definition, it is lower by the SNR, signal to noise ratio. Okay, so I'll just plot it here. So this is my ground level. I'll plot the sensitivity. This is your integrated noise, P integrated noise, and I'll call sensitivity as this level. This is your P sensitivity. Now the noise levels, the interferer levels, interferer tone, let's say I'm applying two interferers. These two are going to create an intermod term whose power will become equal to the noise power, the total integrated noise power. At that point we'll stop and then say this level, okay, this point here is your SFDR, spurious free dynamic range. So this is the other definition for dynamic range in the receivers. Again, I told you this is not something, it's not in the syllabus, but I just wanted to complete it for the sake of completeness of our discussion that we have been having so far. Okay, the other more important thing, which I very briefly mentioned in one of the videos, in one of the lectures itself, is losses. I mean the loss of a band pass filter. Okay, so now whenever we insert a band pass filter after, say for example, an antenna, before it goes to an LNA, we discussed that we need this band pass filter for two purposes. One, it will serve as an input matching system and all that. The second thing is to filter out the interferers. But as a signal passes through this, as it comes at the output, it's going to experience losses. So that losses can be expressed as, let's say, V in square by R in, 4RS is the input power that you're delivering. V out square by 4R out. That I'll use R in here. R in is the input power of this input resistance of the band pass filter. So this is band pass filter. So the output power we discussed for a passive circuit will always be lower. And we also discussed these band pass filters are mostly passive band pass filters. So the output power V out square by 4R out will obviously always be less than or equal to the input power, which is V in square by 4R in. Now again, why am I using 4 here? This is just a definition. So even if for example, LNA has an infinite impedance, this is the maximum available power of the bandpass filter here. Okay, again, this is the maximum available power that the antenna can deliver to the bandpass filter. So I've just used the definition there. The 4 comes from that. Okay, I can also remove 4 for convenience and simply say, V in square by R in is the input power and V out square is the output power delivered by the bandpass filter to an R out output resistance by R out as the output power. Okay, I've used it for notational convenience. I mean, we have been following a certain method, which is available power is what we used for comparisons. Now, loss is defined as the input power divided by the output power. So this will be, loss can be greater than 1, greater than or equal to 1, because input power for a passive circuit will always be more than the output power. For a lossless passive circuit, input power will be equal to output power and loss will be simply equal to 1. Now, we'll just see intuitively what happens when you introduce a loss. This loss meaning, for example, if I introduce a certain voltage level Vx, the output voltage level is going to be Vx upon L. It's going to be slightly reduced. I mean, I've just used a very crude definition here. It need not be this. I mean, you may have to find what is the loss in voltage. I think I should be specific here. It's the power loss what we are talking about. So if I apply a certain power input here, the output power is going to be P in upon L. That's what it means. When you feed this to an LNA, a low noise amplifier, again loss is measured as the ratio of powers, so keep that in mind. And if I refer my input referred noise of the LNA at this point, say VNI square, now if I want to refer it at this point, I'll have to divide it by the power gain. So the VNI square, you'll have to divide it by the power gain. So if I divide it by the power gain here is simply loss itself. So that will be, I'll have to multiply it by L. L is a number greater than 1. Okay, intuitively it should make sense because a bandpass filter is attenuating your signal. You can see it like it's attenuating the signal by a factor of, it can be root L also. I mean, that you have to find out from the power equations, right? So we know from this equation, from the loss equation, you can find what is the voltage level that you will get at the output. If you know the input voltage level, you can find what is the output voltage level. Okay, so from that, the loss VNI square, that is the input noise, into the loss will be your output noise. So here I have assumed the filter itself is noise lossless, but we will come to that a little later now. Okay, so all I am trying to show here is that the noise of your LNA is getting amplified by the loss factor. So if you remember in one of the lectures we discussed that when you cascade noise, when you cascade an amplifier, say with a gain A, and this is V and I is the input referred noise here, I square, we said that the input referred noise at this point is going to be V and I square by A square. It's going to get divided. But because loss, this circuit, the bandpass filter is lossy here, whose gain is less than 1, so the noise gets amplified. I just very briefly mentioned this point in one of the lectures, but I was not sure if you'll remember it or not. So I just quickly thought to mention it now. Okay, so your output power will be, this is out square noise at the outputs, or rather, noise input referred to the bandpass filter input. So the noise at BPF input, I square will be this. Okay, here I've assumed bandpass filter is noiseless. That's the assumption. I haven't included the bandpass noise. Okay, you'll also have to include the bandpass noise and all that. Again, if you go through the Radhavi's textbook, there's a very simple proof. Let's say we cascade a bandpass filter and a low noise amplifier. I'm cascading two circuits and I've given you the noise figure of the LNA. And if I ask you to find what is the noise figure of a bandpass filter with a certain loss, let's say you have a filter with a loss L, then how do we find the, what is the noise figure for this? So it's a very simple proof. I'll just assume that the input is being driven by a voltage source with a finite source resistance into this filter. So the maximum input power that you're going to deliver is Vs square upon 4Rs. Now the filter output, I can model, it's going to have a certain R out. I'm going to model output and a certain R out. And this, for a matched load, the power that it can deliver is simply V out square upon 4R out. Okay, and by definition, the loss in a circuit is simply, the loss of a circuit is simply V in square by V out square. I just have to take the ratio of these two, P in by P out. So I'll get into R out upon R in. So this is the definition of loss, P in by P out, right? P in is simply Vs square by, I'm sorry, I've used V in and Vs here. Hope I conveyed it. So it's simply Vs square by V out square into R out by R in. That's your loss. Now using this, we'll try to compute noise figure of a bandpass filter. Now there is one very important theorem for any circuit. You can, between the two terminals, when you look at it, I'm just going to look at the output of the bandpass filter. I can write it as a Thevenin equivalent. So there is a voltage source and an output resistance. There is also a theorem which is the Thevenin resistance here captures the loss in the circuit. So whenever you have a loss, that's going to create noise. The losses here is going to model the noise. So now I can say that I can treat this entire bandpass filter as a circuit with a resistance of value R out, and the noise is also going to add because of this R out. You are also going to add a noise because of R out. So the output noise is going to be the output noise of the circuit from here to here. It's going to be the output referred noise is because of 4 kT R out. So it's going to be 4 kT. Okay, it's simply going to be I'll actually have to, because normally we'll assume that we are terminating it with a load resistance RL. Okay, and this voltage source I'll model it as the noise itself. It's a Thevenin equivalent, but let me put it in series. So this is your V Thevenin equivalent, or you can when you look at the output of a bandpass filter, it's an electrical circuit. Any electrical circuit, we can model it as a voltage source and resistor in series with it. Okay, now if I connect this to a load resistance RL, this circuit reduces to this. Okay, so if I know the noise here is going to be 4 kT into R out. That's the noise because of the bandpass filter, and that comes because of the losses. R out here captures the losses because of that, multiplied by the transfer function square. I told you the output spectral density at this point can be transfer function square. That is simply RL by RL plus R out. RL by RL plus R out. This is the expression for the total output noise power. For a matched load, we can always find RL equal to R out. It will be just 1 by 4. So that will be just 1 by 4. So this is your output power. Now if I ask you to compute what is the gain of the system, we need to also know the gain, right? So this is the output noise power, noise spectral density. So to find noise figure, I told you first find the output noise divided by the gain. That will give you the input referred noise. That you have to divide it by the input's noise. So now we will look at the input. So this is Vs, Rs fed to a bandpass filter. The bandpass filter is now connected to a load resistance. Now what I will do is, I will assume the input is matched. So it will become Vs by 2 is the input voltage at this point. Okay. Now, so the voltage appearing across at this point is going to be Vs by 2. Or I'll use this gain as this input point is V in. V in is the input fed to the bandpass filter. Okay. So we said that V Thevenin, we could model the output of the bandpass filter as a Thevenin voltage and a resistance R out. Okay, I'll assume a matched load right now, RL equal to R out. So your V out is simply going to be V Thevenin by 2. Okay, that's the voltage across the resistance. The voltage at the input of the bandpass filter is simply V in. So that's going to be V in. So I'll write it as V in, and in that case I can say that it's going to be V in. Input is V in. Okay, so the input of this bandpass filter is V in, output is VTH by 2. So the gain is simply AV, the voltage gain is simply this divided by this. This is your voltage gain. Okay, so VTH by V in, so half into VTH, Thevenin voltage by V in. Okay, so if you find the proof a little fast, I just wanted to give you an idea about the proof. You can go through the textbook as well. If you don't follow it, okay, it's a very trivial proof. You'll easily follow that. It's a very, very simple proof. I'm just making the video so that I can simply ask you to read it, but I thought if there is something which is not clear, I might explain it off. I've made an assumption. Your textbook, they don't make this assumption RL equal to R out, but I have made that assumption. It's very easy to follow the proof that way. The gain here is simply VTH by Vin into half. This should make sense. All I'm saying is the bandpass filter output can be represented as a Thevenin voltage and a resistance in series with it. Okay, so the output voltage will simply be RL by RL plus R out, but I've assumed RL equal to R out, so the output voltage will simply be VTH by 2. That's the output voltage. The input that's going into the bandpass filter is simply Vin. I'm applying an input of Vin to the bandpass filter. So the voltage gain in this case is going to be VTH by Vin into half. Now what I'll do is I'll actually divide this by the gain square. So you have your output noise, which is 4 kT R out into 4 kT R out into half square, which is 1 by 4. I'm going to divide this by this gain square, so which is 1 by 4 into VTH square into Vin square. Okay, I'm going to divide this, so I get this result, VTH square by Vin square. Okay, now this is your input referred noise, input VNI square of this filter. So that result is simply going to be 4 kT R out into Vin square by VTH square. Okay, this is your VNI square. Now to find noise figure, what did we say? That we'll have to simply divide this whole thing by 4 kT RS, which is your RN. For a matched load, it's simply RN. Okay, and then add 1 to it. So it's going to be 1 plus this term. Okay, I think I'll just let me just explain one point here. Dividing is fine, okay, but adding 1, that's the point I wanted to clear it out here. So in this bandpass filter, when I said I can model the output port by a Thevenin voltage source and a resistance R out, the R out here captures the entire noise of the bandpass filter. So that's an important point here. That includes even the effect of RS. So that's what we are trying to tell here. So there is a very standard theorem in microwave theory. You take any two-port system and find the real impedance seen between the two terminals. Then the noise is simply given by 4 kT into R of the real impedance or the losses of the resistive part of the impedance. Okay, so it's actually capturing everything you need to know. Everything you need to know. The noise RS is also captured in it. So R out here is actually the total output noise with RS also captured. Okay, I don't have to do 1. When will I do 1? When will I do 1 is that I'll ignore RS out and then feed 0 as an input to this and then find the noise. In that case, I'll have to add 1 plus, the noise VNI square upon 4 kT RS. That's the case when you're making this noiseless. But this is not the case here. I'm keeping Vs as it is and then computing this. In that case, it's going to be 4 kT into R out. Okay, that will be the total noise. Rn is also included in it. So this is the only point I wanted to explain. That's what your textbook assumes. If you go through the proof, you can see that. Here you will get Vin square by VTH square into R out upon Rn. Okay, so this is a very interesting result. And if you remember, if you see this result is nothing but your loss. So this I've already computed noise figure here, or noise figure is this. I've divided by Rn, okay, R out by Rn or R out by Rs, and for a matched load Rn equals R out, you will get this result. So your noise figure is equal to the loss of the circuit. Loss here is the ratio of the input power by the output power. This is a very interesting fact about this. So when I cascade a bandpass filter and an amplifier, say some low noise amplifier or an amplifier, and I give you the noise figure of this guy, noise figure of this, and we know the noise figure is L here. If I ask you to find the input referred noise, that is going to be the noise figure of the first stage, which is L, plus the noise figure of the second stage, NF minus 1, divided by the power gain of the previous stage, which is 1 by L. Power gain is defined from input to the output. Okay, so which is 1 by L. So power gain, if you remember, it is output power by input power. Okay, and which is nothing but 1 by L, 1 by loss. So you will get NF into L. Or in dB, you can simply add noise figure in dB plus the loss in decibels. So this is a very, very important fact. When you cascade a band pass filter, you are going to add to your noise factor, noise figure. Okay, that's why that's one of the problems. If your band pass filter has losses, that's going to directly add to your noise figure. Okay, so I'll stop at this point. This is the only point I missed out, so you can remember this point as well. This is because this is also a part of noise figure which I didn't cover in the classes. I very briefly mentioned in one of the lectures, so that's why I wanted to cover it now. Okay, I'll stop at this point.